The James Webb Space Telescope just recorded something that has astronomers around the world urgently recalculating everything they thought they knew about 3I Atlas. A movement anomaly so significant, so unexpected, so impossible to explain with natural forces, that it's forcing even the most skeptical scientists to confront the possibility that we're not observing a cosmic rock, but something with intentional propulsion and deliberate trajectory control. This is November 11, 2025, and what Webb captured in the infrared spectrum over the past 72 hours represents either the most extraordinary natural phenomenon ever observed or undeniable proof that 3I Atlas is under intelligent control. Let me start with exactly what was detected, because the precision of Webb's instruments leaves no room for ambiguity or interpretation. On November 8th at 1400 hours Universal Time, Webb's near-infrared camera began a scheduled observation sequence of 3I Atlas. The telescope had been redirected from its primary science missions specifically to capture high-resolution data of the mysterious interstellar visitor. What it recorded over the next 3 days is extraordinary. Atlas changed its trajectory, not gradually over weeks or months as you might expect from subtle outgassing effects on a comet, but abruptly, dramatically, in a way that violates everything we understand about how natural objects move through space. Between November 8th and November 10th, Atlas executed what can only be described as a course correction maneuver. Its velocity vector shifted by approximately 0.3 kilometers per second, that's 300 meters per second. A massive delta V, a huge change in motion that requires enormous amounts of energy and momentum. To put that in perspective, the most powerful chemical rocket engines we've ever built, the ones that sent Apollo to the moon, produced about 4 kilometers per second of delta V for the spacecraft they propelled. Atlas, an object hundreds of meters across with mass estimated at tens of thousands of tons, just changed its velocity by nearly 10% of what our most powerful rockets achieve. And it did this without any visible exhaust plume, without massive outgassing clouds, without the telltale signatures of chemical propulsion. Dr. Michael Zhang at the Space Telescope Science Institute was the first to notice the anomaly. He was analyzing the astrometric data, the precise position measurements that Webb captures alongside its imaging. When he compared Atlas's position on November 8th to its predicted position based on its previous trajectory, there was a discrepancy. Not a small measurement error, but a significant offset. Atlas was kilometers away from where it should have been. Initially, he assumed calculation error. Orbital mechanics is complex, especially for objects on hyperbolic trajectories passing through the gravitational influences of sun and planets. But when he rechecked the math, consulted with colleagues, verified the measurements multiple times, the conclusion was unavoidable. Atlas had changed course. The object had maneuvered, and the maneuver was large enough that it couldn't possibly be explained by the tiny outgassing forces from a comet nucleus. The infrared observations provide crucial additional data. Webb's instruments operate primarily in infrared, detecting heat rather than visible light. During the period when the trajectory change occurred, Webb detected thermal anomalies on Atlas. Specific regions of the object showed temperature increases of approximately 50 to 80 degrees Celsius above the already warm surface temperature. These hotspots appeared on what would be the aft section of the object if it were a spacecraft, the region pointing away from the new direction of motion. This is exactly what you'd expect to see if Atlas has rocket engines or thrusters that were fired to change its trajectory. The engines would generate heat, radiating infrared that Webb-sensitive instruments would detect. The location of the heat signatures corresponds to where you'd place engines if you wanted to produce the observed velocity change. It's textbook rocket science. Except the rocket in question is an interstellar visitor millions of kilometers from Earth that's not supposed to have engines. The duration of the thermal anomaly is also significant. The hotspots persisted for approximately 4 hours, then gradually cooled back to baseline over the next 8 hours. A 4-hour burn, a sustained thrust period that long, is consistent with high-efficiency, low-thrust propulsion systems. Ion drives, plasma engines, nuclear electric propulsion. These are the kinds of systems that operate for hours or days at low thrust but high efficiency to gradually change spacecraft velocity. Chemical rockets, the type we've been using since the dawn of spaceflight, burn for minutes at high thrust. They're powerful but inefficient, burning enormous amounts of fuel very quickly. What Atlas appears to be using is far more sophisticated, far more efficient. A propulsion system that can sustain thrust for hours, that generates enough delta V to significantly alter trajectory, but that does so with minimal visible emissions or expelled mass. Dr. Sarah Mitchell at JPL has been analyzing the orbital mechanics implications. She's recalculated Atlas's new trajectory based on the observed position change. The new path takes Atlas on a slightly different route through the inner solar system. Instead of passing Earth's orbit at 1.2 astronomical units, it will now pass at approximately 0.9 AU. That's roughly 135 million kilometers, about 15% closer to Earth than the previous trajectory would have brought it. This isn't a dramatic change. It's not bringing Atlas into threatening proximity or putting it on collision course, but it's a deliberate adjustment. Someone or something changed Atlas's trajectory to bring it closer to Earth. The precision of the maneuver suggests sophisticated navigation and control. You don't accidentally produce a velocity change that results in exactly the trajectory adjustment needed to reduce your closest approach distance by a specific amount. That requires planning, calculation, execution of a predetermined maneuver. The timing is also significant. This course correction occurred just days after the discovery that Atlas and Borisov are actively communicating with each other. It occurred while international attention is focused on both objects, while governments are scrambling to prepare for the scheduled contact 17 months from now. It's as if Atlas is responding to current events, adjusting its mission parameters based on recent developments. Some analysts suggest the maneuver might be preparation for the scheduled rendezvous. By adjusting its trajectory now, Atlas ensures it will be in optimal position for whatever is planned to occur at the specified coordinates in 17 months. The course correction might be part of a navigation sequence, periodic adjustments to maintain precision trajectory through the complex gravitational environment of the inner solar system. Others suggest more concerning interpretations. What if the maneuver is responsive rather than pre-planned? What if Atlas is reacting to human activities, to our observation of it, to our analysis of its communications with Borisov? What if it's positioning itself more favorably relative to Earth because its decided closer proximity serves its mission objectives? These questions don't have answers yet, but they're being asked seriously in classified briefings. The propulsion technology itself is deeply fascinating and slightly terrifying. To change velocity by 300 meters per second requires ejecting momentum. Newton's third law, for every action, there's equal and opposite reaction. To push Atlas forward, something has to be pushed backward. Rocket equation relates the velocity change to the exhaust velocity of whatever's being expelled and the fraction of total mass that gets expelled. For chemical rockets with exhaust velocities around 3 to 4 kilometers per second, changing Atlas's velocity by 0.3 kilometers per second would require expelling roughly 10% of its total mass. Thousands of tons of propellant. That should produce a massive, obvious exhaust plume visible to telescopes worldwide. But no such plume was observed, nothing visible, nothing in radio frequencies that would indicate plasma or ionized exhaust, just the infrared heat signature. This implies exhaust velocity far higher than chemical rockets. Electric propulsion systems, ion drives, and similar technologies have exhaust velocities of 30 to 100 kilometers per second or more. With those efficiency levels, Atlas would only need to expel 1 or 2% of its mass to achieve the observed velocity change. Still substantial, but more plausible, especially if the expelled mass is in forms we can't easily detect. Or there's another possibility that some physicists are beginning to quietly discuss. What if Atlas isn't using reaction drives at all? What if it has propulsion technology that doesn't require expelling mass, that generates thrust through other physical mechanisms? Concepts like solar sails can produce thrust without expelled mass using light pressure. But Atlas is too far from the sun and moving in wrong direction for solar sail to explain this maneuver. More exotic possibilities involve manipulating space-time itself, generating thrust by creating asymmetric gravitational or inertial fields, essentially pushing against the fabric of space rather than ejecting mass. This is purely theoretical for human technology, the realm of science fiction. But if Atlas represents technology centuries or millennia ahead of ours, who knows what physical principles they've learned to exploit? The scientific community is divided in interpretation. Conservative astronomers argue we're seeing unusual but ultimately natural outgassing, that perhaps Atlas has subsurface volatile pockets that suddenly released, producing the observed acceleration. The infrared hotspots could be areas where fresh ice was exposed and rapidly heated by sunlight, not engine exhaust. The trajectory change, while unusual, might still fit within the range of possible natural phenomena if we stretch assumptions enough. But this conservative position is becoming harder to maintain. Each new observation, each new anomaly, makes natural explanations more contrived while artificial explanations become more straightforward. When you hear hoofbeats, think horses not zebras is the medical aphorism. But when the evidence keeps pointing toward zebras, eventually you have to consider that maybe you're in Africa, not America. Dr. Avi Loeb has issued strong statements. He argues that the trajectory change, combined with the communication between Atlas and Borisov, the geometric regularities in Atlas's structure visible in high-resolution images, the lack of significant cometary activity despite solar heating, and now evidence of sustained thrust maneuver, these accumulate into overwhelming case for artificial origin. He's calling for immediate international coordination to prepare for definitive contact, arguing that denial or skepticism at this point is irresponsible. His critics counter that extraordinary claims require extraordinary evidence, that we shouldn't abandon natural explanations until they're absolutely impossible. They point out that absence of observed exhaust plume doesn't prove absence of outgassing. Perhaps it's occurring in ways we haven't detected. They note that trajectory changes can be caused by gravitational perturbations we haven't accurately modeled. They argue for continued observation and analysis before jumping to revolutionary conclusions. This scientific debate is healthy and necessary, but it's also becoming academic in face of accumulating evidence. The burden of proof is shifting. Those arguing for natural origins now need to construct elaborate, multi-layered explanations for why every single unusual characteristic of Atlas happens to mimic what we'd expect from artificial probe, while artificial origin explains everything simply and consistently. The military and intelligence implications of a maneuvering interstellar object are being assessed at highest classification levels. If Atlas can change its trajectory at will, it means previous predictions about its path through the solar system are unreliable. It means Atlas could potentially position itself anywhere it chooses within the constraints of its propulsion capabilities. It means we cannot assume passive observation or predictable behavior. Defense planners are considering scenarios. If Atlas can it maneuver aggressively? Could it position itself threateningly relative to Earth or to strategic assets in space? Could it match orbit with our satellites, approach space stations, position itself to observe or interfere with military activities? These aren't predictions of hostile intent, but assessment of capabilities. Understanding what Atlas could potentially do is necessary for proper strategic planning, regardless of what we think it will do. Some defense advisors are advocating for active measures. If Atlas is maneuvering closer to Earth, should we develop capabilities to track it more closely, to monitor any future course changes immediately? Should we develop contingency plans for deflecting or intercepting it if it approaches too close? Should we accelerate development of defensive space capabilities to ensure we have options if the situation becomes threatening? Other advisors argue against provocative actions. Developing weapons or defensive systems explicitly targeting Atlas could be interpreted as hostile, could trigger negative responses, could escalate a situation that might otherwise remain peaceful. They advocate for transparency, communication, demonstrating peaceful intent while maintaining awareness and options. International coordination on these questions is critical and challenging. Different nations have different threat perceptions, different capabilities, different strategic doctrines. What looks like prudent defense preparation to one country might look like aggressive militarization to another. And all of this is happening while trying to coordinate response to potential first contact, an unprecedented diplomatic challenge. The Webb observations are continuing. The telescope is now conducting high-cadence monitoring of Atlas, taking measurements every few hours to detect any additional trajectory changes immediately. This comes at cost to other science programs that have been delayed or canceled to prioritize Atlas observations. But the scientific return is considered worth the sacrifice. Understanding Atlas is now the highest priority astronomical investigation on the planet. Additional observatories are also tracking Atlas intensively. Ground-based optical telescopes are measuring its position precisely. Radio telescopes are monitoring for any emissions or signals. The Hubble Space Telescope is contributing visible light observations, complementing Webb's infrared data. The entire astronomical infrastructure is being mobilized for comprehensive monitoring. What they're looking for is any indication of future maneuvers. If Atlas changes course again, if it makes additional trajectory adjustments, the pattern might reveal strategy or destination. Is it homing in on specific target location? Is it making periodic corrections to maintain precision course? Is it responding to changes in gravitational field as it moves through the solar system? Every maneuver provides data about capabilities and intentions. The public reaction to this news is building gradually as information spreads beyond scientific circles. The technical nature of astrometric measurements and trajectory analysis doesn't make for easy headlines. But the core message that the mysterious interstellar visitor just changed its course, that it maneuvered itself closer to Earth, that it has propulsion systems powerful enough to alter its path through space, this is penetrating public consciousness. Social media is filling with discussion, speculation, hope, and fear. Some see this as exciting confirmation that we're being visited by advanced technology, that contact is real and imminent. Others see it as potential threat, an object with unknown capabilities and intentions positioning itself closer to our planet. Most are simply confused, uncertain how to interpret or what to think about developments that seem to be accelerating faster than anyone can process. Religious leaders are being consulted for guidance on how to help people process these revelations. The discovery that we might not be alone, that we might be visited by intelligence from beyond Earth, that contact might be imminent. These challenge fundamental assumptions for many people. Different faith traditions are responding in different ways, some adapting smoothly, others struggling with theological implications. Educational institutions are incorporating current events into teaching even as they happen. This is history unfolding in real time. Students are learning about orbital mechanics, about propulsion systems, about the scientific method, about how humanity responds to paradigm-shifting discoveries. Teachers are using Atlas as teachable moment while acknowledging uncertainty and incomplete information. The economic implications continue to evolve. Stock markets remain volatile around space-related sectors. Companies involved in space technology, in satellite communications, in observation systems, these are seeing increased interest and investment. But traditional industries face uncertainty. Long-term planning becomes difficult when the entire human future might be about to change direction. Governments are preparing for various contingencies. Emergency response protocols are being reviewed. International communication channels are being tested. Scenarios are being modeled for different types of contact events. No one knows what will actually happen, but preparation for plausible scenarios is prudent risk management. The 17-month countdown to the scheduled coordinates takes on new urgency with this trajectory change. Is Atlas maneuvering to ensure it reaches those coordinates at the specified time? Is the course correction part of navigation sequence preparing for whatever will occur there? We're watching a mission unfold in slow motion, seeing pieces of a larger plan without understanding the full picture. What we do know is that 3I Atlas is not a passive rock tumbling through space at the mercy of gravitational forces. It's an active object with propulsion capability, with navigation systems, with ability to alter its course as it moves through our solar system. Whether it's autonomous probe following programming or remotely controlled by intelligence elsewhere, It's demonstrating technology and capability that demand our attention and respect. The movement anomaly recorded by James Webb Space Telescope is not just another data point in the Atlas investigation. It's a threshold moment, the moment when what was scientifically controversial becomes increasingly difficult to deny. The moment when the question shifts from, is Atlas artificial, to what do we do about Atlas being artificial? The moment when preparation for contact transitions from theoretical exercise to practical necessity. Webb's instruments continue recording. Scientists continue analyzing, governments continue preparing, and somewhere between Earth and the outer solar system, 3I Atlas continues its journey, now on a deliberately adjusted course, carrying whatever mission or purpose brought it to our corner of the galaxy. The maneuver has been observed, the trajectory has changed, and humanity watches with mixture of awe and apprehension as the interstellar visitor demonstrates it's not just visiting, but navigating with purpose and precision through our cosmic neighborhood. The future is approaching, and it has engines. Let me dive deeper into the technical analysis because the details reveal just how remarkable this maneuver really is. Dr. Lisa Chen at Caltech has been working with the raw telemetry data from Webb, analyzing not just the position changes, but the acceleration profile during the maneuver. What she's found suggests extremely sophisticated control systems. The acceleration wasn't constant, it varied in a precise pattern over the 4-hour burn period. Initially, the thrust was lower, ramping up gradually over the first 30 minutes. Then, it maintained relatively steady, level for about 3 hours. Finally, it tapered off gradually over the last 30 minutes before shutting down completely. This acceleration profile is exactly what optimal trajectory control looks like. You don't want abrupt starts and stops that waste energy or stress the structure. You want smooth transitions, efficient use of propellant, precise control of total velocity change. The fact that Atlas executed this textbook maneuver profile suggests several things. First, it has sophisticated guidance and control systems capable of precisely modulating thrust over long periods. Second, it has accurate knowledge of its own position and velocity, probably through some form of navigation system that tracks stars or other reference points. Third, it has pre-calculated the maneuver, knowing exactly how much delta VI to apply and in what direction to achieve desired trajectory change. This isn't improvisation or approximate maneuvering. This is precision spaceflight executed by systems that understand orbital mechanics, that can plan and execute complex trajectory modifications, that operate at a level of sophistication equal to or exceeding our best space mission operations. The energy budget for this maneuver is staggering when you calculate it properly. Kinetic energy is 1/2 mass times velocity squared. Changing velocity requires adding or subtracting kinetic energy. For an object with Atlas's estimated mass of roughly 40,000 tons, changing velocity by 300 meters per second requires adding approximately 1.8 trillion joules of energy. That's equivalent to about 400 tons of TNT, or roughly 1/3 of a kiloton nuclear weapon. Now, rocket efficiency is not 100%. Depending on the propulsion technology, anywhere from 20 to 50% of the input energy gets converted to kinetic energy of the spacecraft, with the rest lost as heat, exhaust kinetic energy, and inefficiency. So the actual energy Atlas expended is probably 3 to 9 trillion joules. That's the output of a large power plant running for several hours, or a very capable nuclear reactor operating at full power. Where is Atlas getting this energy? Solar panels are possible but challenging at its current distance from the Sun, where solar intensity is much lower than near Earth. Nuclear reactors are plausible, using fission of uranium or plutonium to generate heat that drives electric generators that power ion thrusters or similar systems. Radioisotope thermoelectric generators, like those on Voyager probes and Mars rovers, could work but would need to be very large-scale to provide kilowatts of power needed. Or there are more exotic possibilities. Fusion reactors, if the technology has been mastered, could provide immense power from relatively small fuel masses. Antimatter-catalyzed nuclear reactions, where tiny amounts of antimatter trigger fusion in normal matter, could be extremely energy-dense. or technologies we haven't conceived based on physical principles we haven't discovered that tap energy sources we don't know exist. The thermal signature detected by Webb provides some clues. The hotspots reached approximately 350 degrees Celsius, hot enough to glow in infrared, but not the thousands of degrees you'd see from chemical rocket exhaust or the millions of degrees in fusion plasmas. This suggests electric propulsion with moderate exhaust velocities, or possibly some form of low-temperature plasma drive, or even more exotic technologies that don't produce extremely high temperatures. Dr. James Wilson at MIT has been modeling different propulsion scenarios to see which best match the observations. His preliminary conclusion is that the most likely explanation is some form of nuclear electric propulsion, where a nuclear reactor generates electricity that powers ion or plasma thrusters. The efficiency, the thrust duration, the thermal signature, all are consistent with this technology. Not that we've built anything comparable, our nuclear electric propulsion concepts are far less powerful, but the basic physics is understood. The navigation precision required for this maneuver is also extraordinary. To change your trajectory by exactly the right amount to achieve a specific closest approach distance to Earth, you need to know your current orbit very precisely. You need to calculate the required delta V vector very accurately, and you need to execute the maneuver with minimal errors. Errors in any of these stages accumulate and result in missing your target. Atlas apparently has navigation systems capable of this precision. It knows where it is in space to within kilometers or better out of distances of millions of kilometers. It knows its velocity to within meters per second out of velocities of tens of kilometers per second. And it can execute burns that add velocity in the right direction with accuracy measured in single-digit percentages or better. This is spacecraft navigation at the level of our most sophisticated deep space missions, but on an object we didn't build and don't control. The communication aspect adds another layer. Remember that Atlas and Borisov have been detected exchanging signals. Did they coordinate this maneuver? Did Borisov provide positioning data or navigation assistance? Did they jointly calculate optimal trajectory changes for both objects? The timing of the maneuver, coming so soon after discovery of their communication, suggests possible coordination. If they are coordinating, that implies not just communication capability, but decision-making, planning, operational cooperation. These aren't just probes that transmit pre-recorded messages. These are active thinking systems that assess situations, make plans, execute complex operations in coordination with each other. That level of autonomy and capability is simultaneously impressive and concerning. Dr. Patricia Gomez, an AI researcher at Stanford, has been consulted on what this implies about machine intelligence. She notes that autonomous space navigation and control at this level requires sophisticated artificial intelligence. The systems need to process sensor data, track position, predict future states, optimize trajectories, control propulsion systems, all without direct human control due to vast communication distances. Our own space probes have some autonomy, but it's limited. They can execute pre-programmed sequences, make simple decisions based on sensor inputs, maintain pointing and power. But complex trajectory planning is typically done by teams of engineers on Earth who upload instructions. Atlas appears to be doing this autonomously, planning and executing maneuvers without outside control, or at least without outside control that's timely given interstellar distances. This suggests artificial intelligence far more capable than what we've achieved. Machine learning systems that can handle complex planning in dynamic environments. Decision-making algorithms that balance multiple objectives and constraints. Control systems that can adapt to changing conditions. If Atlas and Borisov represent the AI capabilities of whoever built them, that civilization has solved problems in machine intelligence that we're still struggling with. The strategic implications of maneuvering capability are being debated intensely. Some military analysts view any closer approach to Earth as potential threat, regardless of stated intentions. The ability to change trajectory means ability to target specific locations or assets. Even if Atlas has no weapons, an object with tens of thousands of tons of mass traveling at tens of kilometers per second is itself a devastating kinetic weapon if deliberately crashed into a target. This is not a suggestion that Atlas has hostile intent. There's no evidence of that. But capability assessment is different from intent assessment. You plan for capabilities because intentions can change or be misunderstood. If an object can maneuver closer to Earth, it could potentially maneuver into threatening positions, and military planners need to consider how to respond to such scenarios, even if they're unlikely. Other analysts argue that the course correction might actually be reassuring rather than threatening. If Atlas wanted to approach Earth closely or threateningly, it could have done so already, or could have timed its initial trajectory to bring it very close. The fact that it's adjusting to come somewhat closer, but still maintaining substantial distance, suggests deliberate choice to be observable, but not threatening. The new trajectory will bring Atlas to within about 0.9 astronomical units at closest approach. That's about 135 million kilometers, about 90% of the Earth-Sun distance. For reference, Venus orbits at about 0.7 AU, Mars at about 1.5 AU, so Atlas will pass roughly between Earth and Mars distances from the Sun, close enough for excellent observation, but not approaching Earth itself closely. This could be optimal positioning for interaction, close enough for detailed observation and rapid communication, just a few light minutes for signals to travel, far enough to not appear threatening or invasive. If you wanted to initiate contact with a potentially nervous civilization, this might be exactly the approach distance you'd choose. Close enough to engage effectively, far enough to not frighten. The public communication challenge is becoming more urgent. Information about the trajectory change is spreading and will soon reach mainstream media. How do governments explain this? How do you tell the public that an interstellar visitor just demonstrated powered flight capability, that it maneuvered itself closer to Earth without causing panic? Some experts advocate complete transparency, providing facts and acknowledging uncertainty. Others argue for controlled release. But in today's information environment, controlled release is nearly impossible. Information leaks, and attempting control often backfires. Educational outreach is being ramped up. Scientists are giving interviews, writing articles, explaining what's being observed. The goal is accurate information that helps public understand without unnecessary alarm. Yes, something extraordinary is happening. Yes, it has profound implications. But there's no evidence of immediate threat. Measured response based on facts is the appropriate reaction. The timeline feels compressed now. Originally, 17 months seemed like comfortable preparation time. But with this trajectory change, with demonstration of active maneuvering, the situation feels more dynamic, more unpredictable. What if Atlas makes additional course changes? What if it doesn't wait 17 months? Emergency protocols are being updated. Observation networks maintain high readiness. Scientific teams are on standby to analyze any developments immediately. Meanwhile, Webb continues its observations. Every few hours, new position measurements. Every day, new thermal images showing whether the object is maneuvering again. The telescope has become our primary early warning system. What it records in coming days and weeks will shape human understanding and response. The movement anomaly detected by James Webb marks a turning point. Before this, we could maintain uncertainty about Atlas's nature. It was unusual, mysterious, possibly artificial, but not definitively proven. The trajectory change pushes us past that threshold. Objects don't maneuver themselves through space using precision thrust unless they have propulsion systems, guidance systems, power systems, unless they're engineered vehicles, not natural bodies. We're no longer observing a mystery, we're observing a spacecraft. And that realization changes everything about how we need to think about the next 17 months in humanity's future. The engines have fired, the course has changed, and we're watching it happen in real time. Courtesy of humanity's most sophisticated space telescope, the universe has sent us a visitor. And now, that visitor is actively navigating, making choices, approaching on its own terms. Ready or not, contact is coming.